In the last lecture, we had discussed the stress tensor. The stress tensor is related to the flux of momentum. Okay. If you recall, we had said that the flux of mass and the flux of energy, they are both vectors. They have magnitude and direction. The direction is the direction along which mass or energy is transported. In the case of momentum, momentum itself is a vector in contrast to mass and energy, which are scalars. Therefore, there is a direction associated with the momentum itself, and there is a direction associated with the direction of transport of momentum. Okay. So, for example, if you have a Cartesian coordinate system, you could have, for example, x momentum transported in the x direction, you could have x momentum transported in the y direction, and similarly in the z direction, and so on. Okay. So, formally the stress tensor is defined such that it is defined using two unit vectors. I had written it in matrix notation in the previous lecture as okay. So, that is what I had written, the stress tensor in matrix notation, and in this case sigma times x times y. Okay. Okay. This is equal to force per area in the x direction, okay, acting at a surface with outward normal in the y direction. That is the definition. Okay. So, sigma xx is the force per unit area in the x direction acting as a surface with outward unit normal in the x direction, and so on. Okay. So, if I have a surface S with some particular unit normal n, okay, if I have a surface S with some particular unit normal n, and I want to find out what is the force acting at this surface. Okay. If this is a differential surface delta S, of course, the force itself will be proportional to delta S. Okay. So, therefore, the force vector, okay, acting at the surface is equal to sigma dotted with the unit vector times delta S. Okay. That is a force acting along the outward unit normal. The outward unit normal is a force that is exerted on the volume below. Okay. The volume below has an outward unit normal n. So, therefore, this is a force that is exerted on the volume below the surface if the outward unit normal is in the positive direction. Okay. So, that is the definition of the stress. Okay. Note that this is along the outward unit normal, therefore, the force, the stress as defined is extensional. Okay. It acts along the outward unit normal, that means that it is extensional. So, for any differential volume, the force that exerts along the outward unit normal, okay, is extensional in nature, whereas it is compressional if it is along the inward unit normal. Okay. So, this is what we had defined as the stress tensor in the previous class. Force per unit area in the I direction acting at a surface whose unit normal is in the y j direction is sigma I j. Okay. So, that is the stress. This stress could be acting either internal to the at a surface which is within the flow, or at surfaces which are at the boundaries of the flow. Okay. Either of those, it could act in either of those directions. Okay. So, that is the definition of the stress tensor. I should note here one convention change between the mass flux, the heat flux and the stress. Okay. If you recall, the mass flux J, okay, if I have a surface with unit normal n, okay, and the mass flux is defined as J. Okay. The mass per unit area that is transported across the surface delta S, okay, mass per area transported across surface delta S will be equal to delta S times J vector dotted with the unit normal. Okay. This flux tends to increase the concentration in the volume above the surface. Okay. This tends to increase the concentration in the volume above the surface, because in this case the mass flux is defined as positive for a volume if it is increasing the concentration or the mass within that volume. Okay. Whereas, okay, and for this reason the mass flux is in the direction of the constitutive relation, which is Fick's law, is J is equal to minus d grad C. Okay. It is along the direction of decreasing concentration. Mass tends to move from higher concentration to lower concentration. Okay. In contrast, in this case we have defined it as the force per unit area acting a surface whose outward unit normal is this, okay, whose outward unit normal is in the n direction. That means that this force is increasing the momentum of the volume below. Okay. That means that this force is increasing the volume of the momentum of the volume below. Okay. So, there is greater momentum in the volume below if the stress component of the stress is positive, or if the force is positive, whereas in this case there is a greater concentration in the volume above, greater mass in the volume above. Okay. So, there is a difference in the sign convention that is used for stress as compared to mass and energy transport, that is the mass flux and the heat flux. So, this is a force per unit area in the x direction acting at a surface with outward unit normal in the y direction. Okay. So, that was the definition, and then we had used angular momentum if you recall, we had written angular momentum for a differential volume of width delta x and delta y perpendicular to the z axis. We had written the angular momentum balance, that is the moment of inertia about the z axis times d of the angular velocity by dt is equal to sum of the torques. Okay. And the torques are only due to the stresses that are parallel to the surface. Okay. The reason is because the stresses that are perpendicular to the surface do not exert a torque, because the perpendicular distance to the centroid of this is equal to 0. Okay. So, therefore, you have torques exerted in each of these. Okay. And from that we had derived the relation that since the moment of inertia goes to 0 as delta x square or delta y square, we had derived the relation that sigma x y is equal to sigma y x, sigma x z is equal to sigma z x, and sigma y z is equal to sigma z y. Okay. And this implies that the stress tensor, okay, I will just write the components without the unit vectors here. Yeah. This is symmetric tensor. Okay, this implies that the stress tensor is a symmetric tensor, okay, because the off diagonal components are all equal. Okay, these two are equal, these two are equal, and these two are equal. Okay, so the stress tensor is a symmetric tensor. Okay. And if you recall, I had also defined at the surface the normal force and the tangential force. Okay. So, if you have a surface within the fluid, with outward unit normal given by n, okay, and the force, as I said, is in some direction f. Okay. This force, okay, is equal to sigma dotted with n d delta s, okay, sigma dotted with n delta s. Okay. So, this force can be separated into two parts. One is the force that is normal to the surface, that is the component that is normal to the surface, which I will call f n, and the second component that is tangential to the surface, which I will call f t. Okay. So, the normal component is basically the magnitude of the normal component is basically equal to n dotted with f, okay, which is n dot sigma dot n delta s. Okay. So, this is the normal component of the force. The normal force itself is the component times is the magnitude times the unit vector. Okay. So, this is equal to n into n dot sigma dot n delta s. Okay. So, this is the normal force to the surface along the perpendicular to the surface. Note that each of these n's is a vector, the stress is a tensor, and therefore, I have taken two dot products. Okay. So, basically what I have to do is that in order to just recall how you do this, sigma dot n, okay, is equal to sigma is E x, E y, E z into sigma x x into E x, E y, E z. Okay. This is dotted with the unit vector. Okay. The unit vector, as you know, n vectors equal to n x E x plus n y E y plus n z E z, where n x, n y and n z are the components of the unit vector. Okay. So, I am dotting this with the unit vector, that is n x E x plus n y E y plus n z E z. Okay. Note that it is the second index that corresponds to the direction of the unit normal, and that is what has to be dotted with these unit vectors here. Okay. And if I do that dot product, what I will get ultimately is E x, E y, E z. Okay. Okay. Into n x, n y, and z. That is what you will get if you do the dot product. Okay. And this is what is referred to as sigma dotted with n. Okay. And if I expand it out, what I will get, this will be equal to E x into sigma x x n x plus sigma x y n y plus sigma x z n z plus E y into sigma y x n x plus sigma y y Okay, that is what is meant by sigma dotted with n. And then after that I pre-multiplied by n again. So, therefore, this is equal to sigma dotted with n, and n dot sigma dotted with n I pre-multiplied by n again. Okay, so, I get n x into okay, so that is what this is now a scalar. Okay, so, this is now a scalar, okay, and that multiplied by n gives you the vector. Okay. Therefore, I have the force is equal to sigma dotted with n. Okay. The normal force is equal to n along the unit normal n dot sigma dot n, which implies that the tangential force, sorry, I should put the area here. Okay, I should put delta S. Okay. The normal force is equal to n vector into this scalar n dot sigma dot n delta S, which implies that the tangential force is equal to the total force minus the normal force. Okay. And therefore, the tangential force is equal to sigma dotted with n minus n vector into n dot sigma dot n, whole thing into delta S. Okay. So, that is how you get the components of the force parallel and perpendicular to the surface. Okay. Okay. So, now let us consider what happens for the special case of a static fluid. Okay. If a fluid is stationary, if there is no velocity, right, in that case as well the stress tensor can be in general non-zero, because the static fluid has pressure. Okay. You know that if you have a fluid of certain height h, okay, the pressure at the bottom surface P is equal to rho g times h, where rho is the fluid density, g is the gravitational acceleration, and h is the height. This pressure is present even in the absence of flow. Okay. And as you know, the pressure is compressive. Okay. For any differential volume, the pressure is a force per unit area that is acting perpendicular to the surface. Okay. The pressure is a force per unit area that is acting perpendicular to the surface. Okay. Perpendicular to the surface and compressive. Okay. Therefore, it is a compressive force per unit area acting at the surface. Okay. That is the pressure. It acts only along the unit normal. Okay. We had defined stress as acting along the outward unit normal. Okay. The stress that we had defined it was acting along the outward unit normal. Okay. Okay. The stress as we had defined it is acting along the outward unit normal. Therefore, for a static fluid, the force per unit area acting at any surface has to be along the inward unit normal. Therefore, the stress for a static fluid will have three components, each of which is acting along the inward unit normal. Okay. So, it is E x, E y, E z into minus P 0 0 okay. So, this is the stress tensor in a fluid that is stationary. Okay. there is a pressure, that pressure is compressive, and therefore, the stress is the negative of the pressure as we have defined it here, because we have defined it to be acting along the outward unit normal, whereas the pressure is defined as positive if it acts along the inward unit normal. Okay. So, what this basically means that this is equal to E x into minus P E x plus E y into minus P E y plus E z into minus P E z. Okay. That means, at the surface with unit normal in the x direction, that is the front and the rear surfaces, the pressure is acting along the inward unit normal, therefore, the stress is minus P. There is, so this basically implies that the force is exerted only along the unit normal, and the shear components, that is the force per unit area in the x direction at a surface with unit normal in the y direction is 0. Okay. So, the force is acting only on along the compressive surface. Okay. This pressure, this stress due to the pressure can also be written as minus P times what is called the isotropic tensor, okay, where the isotropic tensor is just the identity tensor. Okay. The diagonal elements are equal, the off diagonal elements are all 0, right. So, the stress tensor is isotropic in this case. Okay. It is equal to minus P times the identity tensor. Okay. Okay. So, therefore, at any surface with unit normal n, right, the force per unit area will be equal to E x, E y, E z times delta S. Okay, I just derived this for you. So, this I will get minus P E x n x minus P E y n y minus P E z n z. Okay. So, if I just do this matrix multiplication, I will get minus P n x in the first row, minus P n y in the second row, minus P n z in the third row, multiplied by the unit vector. This whole thing times delta S, okay. And n x E x plus n y E y plus n z E z is just the unit normal n vector. Okay. So, is equal to minus P n vector delta S. Okay. So, therefore, the force acting at any surface, okay, of some angle with unit vector n, with outward unit normal n, is going to be acting in the minus n direction. This is the force, okay, and the magnitude of the force is going to be equal to the pressure times delta S. Okay. So, the magnitude of the force will be equal to the pressure times delta S. Okay. Now, this pressure tensor is only for in the absence of flow. Okay. In the presence of flow, there will be variations in the stress due to the viscous effects. Okay. Just as there is transport of mass due to concentration gradients, due to diffusion, transport of energy due to temperature gradients due to energy diffusion. There is also transport of momentum due to velocity gradients, okay, due to momentum diffusion, and these are what are referred to as the viscous stresses. Okay. So, the viscous the stress tensor in a flowing fluid can be written as minus P times the identity tensor plus tau, where tau is the viscous stress which is present only in the presence of flow. Okay. And if you recall, when we did mass and energy conservation, we got we wrote down Fick's law for diffusion and Fourier's law for heat conduction. Okay. In a similar manner, we have to get a relation between the stress and the gradient of the velocity field. Okay. In a similar manner, the constitutive relation for momentum should relate the stress to the gradient of the velocity. Okay. Note that the stress is a tensor, it has 9 components. Okay. It has 2 fundamental directions, the direction of momentum and the direction of the variation of momentum. Okay. The velocity gradient is also a second order tensor. Okay. So, let me write that velocity gradient for you. Okay. It is also called as the rate of deformation tensor. Okay, the velocity gradient or the rate of deformation tensor. This is basically the gradient of the velocity. Okay. Gradient is a vector, okay, and the velocity is a vector. Okay. So, if I were to write this in Cartesian coordinates, it would be Ex d by dx plus Ey d by dy plus Ez partial by partial z, acting on Vx Ex plus Vy Ey plus Vz. Note that there is no dot between the two, there is no dot product. So, this is not the divergence of the velocity, this is the gradient of the velocity. Okay. As I have written it, this is the gradient of the velocity field. Okay. So, I can expand this out, I will get Ex partial Vx by partial x Ex plus Ex partial Vy by partial x Ey, okay, plus etcetera. There will be total of 9 terms that will give me Ez partial Vz by partial z Ez. Okay. So, there will be a total of 9 terms here. Okay. And just as I wrote this with the stress tensor, I can also write this in matrix form. Ex, Ey, Ez, okay, and Ex, Ey, Z, partial Vx by partial x, okay, Ex into partial Vx by partial x into Ex, right. So, I will get Ex, that is the first term, partial Vx by partial x into Ex, okay, and the second term will be partial Vy by partial x. Okay. So, therefore, this will give me the second term if I multiply these Ex into partial Vx by partial y times Ey, that is the second term here, okay, and this is the first term, okay, and partial Vz by partial x, okay, partial Vx by partial y, partial Vy by partial y, partial Vz by partial y, partial Vx by partial z, partial Vy by partial z, partial Vz by partial z. Okay. That is the velocity gradient tensor or the rate of deformation tensor. I will give you a physical interpretation of this in the beginning of the next lecture, and then I will discuss how this is decomposed into different components. Okay. So, I will continue this in the next lecture. Okay. I will see you then.